is 18 kilovolt transformers. Okay. Also there are some loads here, load C, load A and load B. So to connect two components, we have to use the bus bar. Okay. Let's say this is one bus bar, this is bus bar 2. It is connecting the generator to this transformer. Okay. Then this bus bar 7, it is connecting this transformer and this load. Okay. So like this, there are many buses in the system. For this diagram, we have 9 buses. Okay. You can see the numbering of 9. Actually, with the bus bar, the one defined voltage is assigned. Okay. So let's say in bus bar 2, it has the voltage magnitude of 18 kV. Similarly, in bus bar 1, it has a voltage of 16.5 kV. Okay. So along with this bus bar, we will get some voltage information. So here, this bus bar is connecting this generator and this transformer. Okay. And here the voltage is V alternator. So in the terminal voltage of this alternator or synchronous generator.
Please slide, do the slide.
Then this is a load. Okay, so in this load, we have to know the voltages. If you know the load voltages, then it is easier for analysis. Okay, actually, bus bar is not bus bar is there in the practical scenario. Maybe it is used to for other purposes, like not directly, but bus bar present in practical purposes. Generators simultaneous for any time, then it is difficult for us to actually understand the consequences in different stability scenarios. Okay, that's why to make our analysis easier, we are considering only one synchronous generator and we are assuming the rest of the networks as the infinite ones. Okay, as this is a large amount of network, so whatever let's say elaborate these things later on. So actually, for this case, infinite bus, our voltage and frequency should be constant, right? That is the concept. Yeah, please. Yeah. Okay. So now, if actually we have to, if I want to say directly, I would say that if this infinite bus delivers any real power or reactive power to this generator, so the amount of real power and reactive power will not be changed inside it, right? So this is a big network. Similarly, if it takes some amount of real power or reactive power from the generator, so the difference will not be any impact on the amount of real power and reactive power that was previously given to this infinite bus. Okay, so if the real power and the reactive power inside it are remain constant, so voltage and frequency will also constant. Okay? You will see the relationship between them. Have you understood this, the concept of infinite bus, while the voltage and frequency actually are constant inside it? Any confusion? Another thing is that actually this infinite bus works as reference. Okay? So whenever we solve some numerical problems, so we set this infinite bus as reference because here the voltage frequency is constant always. We will set it as reference, and keeping it as reference, we have to calculate the other parameters. Okay? That will be our technique. Whenever we will solve some example problems, we will see that we are making this infinite bus as reference. With the voltage, there are some voltage angles, right? So for the infinite bus, we assume that the angle associated with the voltage is zero. Okay. So with that reference, we have to calculate the associated angle with this generator. That is the delta. Okay. That means will come in our next slide. Okay. But I just give you the introductory concept so that you can understand that what topics actually are going to be covered in this course in the future. Can actually give one practical analogy of this infinite bus so that you can understand it in a more better way. Okay? That is, let's say, let's think this infinite bus as a river, okay? And this generator as the boat. Okay? So, if the boatman takes some water from the river, so actually the amount of water in the river will be saved, right? There will be no noticeable amount of decrease, right? Inversely, if the boatman supplies some power and water from the boat to the river, so that increase will not be much indicated in the amount of water inside. Okay. So similarly, infinite bus, whether you take or give any real power or reactive power into it, or you take from it, the voltage and frequency will be kept constant. Okay. That is the main concept. Now, if you understand this diagram, now let's go back to our previous slide. Now look, the rotor angle is static. Okay. It's due to the imbalance between PM and PC. Okay. That is the delta input and delta output. So what is delta input? Right. And what is between the delta output? Okay. power generation and reactive power demand. This is the reactive power generation. This is the reactive power demand. This is the real power. If there is any mismatch between this Q and this QG, okay, so we are calling it as voltage stability. Why? Because the mismatch is for reactive power Q, but we are referring it voltage stability or voltage stability because actually this Q and V are actually strongly coupled to each other. Okay, so if actually Q increases, then V increases. Okay, so know this thing you know from your house diagram. Okay, whenever Q increases, V actually increases. Okay, there is one simple formula that actually gives us the relationship between V and K. That says that V equals to V1 plus KV. Okay, so here V1 is the lower voltage, V is our voltage, and reactive is the reactive power. This K is a positive constant. Okay, that means that whenever you use formula plus sign, whenever this Q will increase, the V increases, right? If Q increases, V also decreases. Okay, so can you relate the Q with V? Okay, that's why the infinite class I was taking that the amount of power, reactive power will be same. That's why the voltage magnitude will also be same. Okay, so if the reactive power generation and demand do not match, at that time we will call it as voltage stability scenario. Okay, then the last case is the frequency stability. So there is any mismatch between the real power demand and generation. That is the PG, is PG, real power generation, and the real power demand P. If there is any mismatch, we will call it as frequency stability because similar as Q and V, here P and F frequency are actually strongly coupled, and there are some relationships. Okay, if P increases, F also increases. If P increases, F decreases. Okay, so that's why the mismatch is for the real power demand, but we are calling it as frequency stability or frequency stability mismatch.
Sir, how is frequency related to the real power?
How?
Is frequency related to the real power?
Real power. So there is one formula that I give. There is some formula like this. Change in frequency which is proportional to the change in real power. And there is one parameter that will be handled like this. So using this formula actually the frequency changes in terms of the real power. Okay. But as well as from the house diagram, you can also observe this thing. Okay. Whenever the real power increases, the frequency decreases. So I think you can again go to the house diagram of that. At that time we really understand the relationship between P and Q as well as the P and Q. Okay. So any other questions? This diagram is called the single line diagram. And in this course, our 90% contents will be based on this diagram. That is the single machine connected to infinite bus. This system is called single machine infinite bus system. Shortly, SMIB system. We will see this in our next slide as well. This is called the single machine infinite bus system. Then there is one slide where actually we will study about the two machine system. So if we increase the number of machines in our study, then there will be obviously some complexity. Okay. So we will also go through that slide that the two machine systems are, except that all the study will be based on the single machine system. Okay. Okay. So if there is no question, I think we can move to our last slide. So this is the consequences of instability. Okay. So we should actually understand the effects or the consequences of instability. Okay. Otherwise, we will not realize the importance of instability. Okay. So let's say this is a network diagram. Okay. Here actually you can see there are three generators, right? Here one, this is two. From the number of generators called the gate machine system. As there are 3 generators, we will call it as 3 machine system. And here the number of buses are 9. So we will call it as 3 machine 9 bus system. Okay. So I have already discussed about the bus and also about the transformer. This is the transformer. Okay. We know this parameters. So this is the transformer we have decided, like J.0625. This is the this bus voltage. Okay. Like this. Now look, this is the transmission line. So here something is written over here, right? 0.0085 plus J.070. The first portion is the resistance, and the next portion is the reactance. Okay, combining this model with our impedance. Then there is something written over here. This is the B value. Okay. You know what is B? What is B? This is the transmission line properties. So which are the properties of transmission lines? Resistance, reactance. Is it any other thing like weight?
ABCD parameters. There are some parameters ABCD.
ABCD parameters is another thing, but this is related to resistance, reactance, kind of these things. Maybe you say that susceptance, right? Yeah, this is the susceptance, shunt susceptance or shunt capacitance. Okay, this is actually the shunt capacitance B. But why we divided it by 2? Any idea?
There are some concepts for long transmission and medium transmission. We lump them together and
Exactly. So actually in your power system course, maybe you have learned that there are some classifications of transmission lines in terms of length. Okay, like short transmission line, then medium transmission line, and long transmission line. So for the short transmission line, the assumptions are that we actually created the resistance and reactance. Okay, so you do not care about the resistance and reactance. You only care about the shunt capacitance. For the medium line transmission line, actually this diagram is for the medium line transmission line, where the transmission line is maybe in the range of 20 km to 85 km. At that time, we have to consider the resistance as well as the reactance, okay, and also the shunt capacitance. And for the medium line transmission line, there are 2 models, I model and G model. Okay, so in those 2 models, actually, it is assumed that our shunt capacitance will be split into 2 portions, and one portion will go to the sending end and one portion will be allotted for the receiving end. Okay. Whenever we will do the load flow of this diagram, let's say we know all the voltages here and all the parameters, so we can run the load flow analysis, right? So after the load flow, what will be our solution? We will get some power flow direction, right? With the amount of power that are actually coming out or coming in to any class, right, or to any class. Let's say this is the directions. Okay, here all the directions and the arrows that I will write here. So this is just the arbitrary arrows of directions. Okay, this is not the calculated directions. So let's say this is the scenario of our power flow solution, and this is the directions. So either depending on the power flow solution, either this line will be sending in or receiving end. Okay, so it will be only one, either sending end or receiving end. That's why here it is created by divided. Okay, here also it is divided. Across all transmission lines, here divided is created. And for the long transmission lines, actually the calculation is difficult. We will not go into that. Okay, so this is our network. So there are another thing, the load. Okay, so there are 3 loads. Load C, load B, and load A. There are 3 loads. Okay, so this is HV machine, 9 bus system. So we have transformers, transmission lines, and then actually the load. Okay, that 3 buses, bus 8, 5, and 6. Now another thing, actually here all the resistance, reactances, and the shunt capacitance are lumped into a discrete point. Okay, have you ever heard about the term lump? Do you know the lump network? What is meant by this lump network? Can you know? loads, we use on this type of circuit. Yes, this is zero circuit. So therefore, 2 ohm into this is the transmission line, right? If I want to say that is there any voltage difference between these 2 points, we will say that no, right? Assuming that there is no resistance here, right? But think about one transmission line. So inside the transmission line, the resistances or reactances or shunt capacitance, all the currents should be distributed over the line continuously. It shouldn't be at some point and then shouldn't be present at another point. Not like that. Rather, the transmission line should have the resistances, reactances over the line, okay, continuously. But for our calculation to make it easier, we consider that we actually consider it as Lam's network. Lam's we put together into some discrete points. Let's say there are resistances across the transmission line, but we are actually thinking that okay, so 2 ohm is here only in this discrete point, then 3 ohm is here, and in other lines there are no resistance or reactance because we have actually marked all the resistances into these 2 discrete points. Okay, so that is the concept of Lam's network. Have you understood this thing? So actually here as well, as though the resistances, reactances are distributed over the line, but it is considered as Lam's network. That's why all the resistances, reactances are here in this portion. Okay. So now I think we have described this diagram. Now let's go to the consequences of stability. Okay. Let's say we have load demand here of 100 kilowatt. How to satisfy this load demand by these components? By these 3 generators, right? Let's say this generator is providing 40 kilowatt supply, and from this generator we are getting 80 kilowatt supply. Let's say from this generator we are getting 80 plus 80 plus 40, so 200 kilowatt load demand are being satisfied. So, and these 3 generators are the synchronous generation, right? So, synchronous generator runs at synchronous speed. That is represented by NS. Okay? NS. And there is one total formula for NS. That NS will be equal to 1 divided by 3, right? It is the number of poles and this is the nominal frequency at which the generator is operating. The system is operating. For our countries, 50 hertz. Maybe for other countries, it may have 60 hertz. Okay, so let's say there is some disturbance in the rotor angle of this generator 2, and for that reason, this generator 2 is not running at synchronous speed. Whether it is running at different speed and continuously changing its speed. Okay, that is the actual dynamic. It is going to the dynamic state. Okay, stable state. Okay. Now, remember that across each of the component there are some protective equipment like fuse or circuit breakers. Okay. So whenever there is any fault in a particular component, what will be the first task of the protective equipment? And you must to isolate that unhealthy part from the healthy portion of the network, right? So there are some protective equipment here, right? So whenever there is some disturbance in the rotor angle of the generator 2, so the protective equipment associated with this generator will immediately disconnect this generator from the system. Okay? Now this generator is disconnected from our system. Okay? And this sudden connection is called as generator tripping. Okay? So what is tripping? Tripping is the sudden disconnection from the network let's say due to the disconnection of this generator, we will have the deficit of this 40 kilowatt, right? That was generating or supplying from this generator. But our load demand is still 200 kilowatt. So what will be the probable solution? How can we meet the load demand? Yeah, load shedding is one scenario. This is the last solution. Whenever we are not capable to do any kind of solution, we will share some amount of load from the system. But should we have any other options? Because there are two generators, right? So we can increase the supply power from these two generators, right? So this can be the best option. Okay. So let's say I am giving extra 20 kilowatt generation from this generator as well as 20 kilowatt from this generator. Okay. So now the load demand and total generation is same, right? 200 kilowatt. Now, before the fault case or in the pre-fault scenario, this generator was providing 40 kilowatt. This was and this was it. At that time, we can solve the load flow, right? You will get some power flowing across any transmission lines, okay, with its duration. We will get that information. Let's say at that time, the power flowing through this transmission line is 20 kilowatt, okay. And after fault, now this generator is disconnected, and this amount of power is delivered now by sharing of these two generators by 20 kilowatt and 20 kilowatt. Okay. Now we can again solve our load flow, right? And now we will get a new set of solution, right? We will get an updated power flow, right? Okay. So that's why our power flow is ampered. Okay. This scenario is called the ampered power flow, because due to the new scenario, we have to again calculate the load flow and the power flow will be updated. Okay. So this is called the ampered power flow. So due to this ampered power flow, let's say previously in the pre-fault case, this line was taking 20 kilowatt. Okay. And after the fault, actually now in the updated power flow solution, you are getting, let's say, this all of actually this all of these values are actually arbitrary. Okay. So you know, take these values as calculated values. Okay. Let's say in the post-fault scenario, now the updated power flow solution gives us 20 kilowatt power flowing through this transmission line. Okay. Now for each transmission line, there is a limit of power flow. Okay. So let's say the limit for this transmission line is 22 kilowatt. That means it can take up to 22 kilowatt power flow. Okay. If the power flow is beyond that, this transmission line will not be capable to take that. Okay. So now the power flow is 25 kilowatt. So according to the scenario, according to the consequences, this line will be broken. Okay. This line actually can take this high amount of power, so it will be broken immediately. So if this line is broken, then the bus 8 and the bus 7 will be disconnected, right? Because this was the connection. So these two will be separated. Now, if this generator 1 wants to supply the power at load C, previously maybe there was two paths, right? This path and this path. It can reach up to this load, but after disconnection of this line, now there is only one path, right? Only through this path it can reach the power supply to this load within this path. Okay. So it may happen that again this transmission line may be overloaded, right? Because all the power flowing is now coming through this line. If again this is overloaded, then this line will be broken down. So load C is now completely disconnected from the generator sources, right? So there will be some outage or load shedding here. Outage is the complete load shedding. There is no supply provided to any particular load demand. That is called the outage. Okay. So this line is broken. This is now in the outage scenario. If this line breaks actually, okay, then powerful solutions, and at that solutions maybe some other lines will be overload, right? So let's say all of these lines are breaking. Okay. So this phenomena is called the cascaded outage. So what is the cascading? Cascading means that one event is relevant to the previous event. Actually, one event is occurring due to the previous event, then another new event will be occurred due to the previous event, like this. Okay. So as one transmission line is breaking down, then after that others are also breaking down. So this scenario is called the cascaded outage. Okay. So this point is clear to you, right? Any confusion up to now?
So if the asking for the transmission is how to the power.
No, only these lines go. Okay. Then there is the necessary part. Yeah, then there will be no power, right? Going that way. Okay. So if light is away, all of the transmission lines are breaking down, then all these load A and load B and load C, okay, will go to the outer system. Okay. So in the system, there are only three loads, but no supply, right? So this system is called the system download. The system download as all the lines are breaking down, like this load C, load B and load A will not also make any power supply for the generator, right? So all the load demand will work, all load demand should be now down. So power supply is given to the end of the load. Okay, that's why this is called the system block. It is system block. Now if this system have you understood the cascade outage?
System record చేయటం
Set of solution for power flow. We are getting that we are seeing that this line is broken into the overloading condition, right? So for this another line will be overloading, right? And we will be disconnected. Like this way, all of the transmission lines will be taken care. Okay? So that's why load C and load B and load A, all the loads will go to the complete load sharing scenario. Okay? There will be no power. There will be no power in any of them. Okay? This scenario is called the system blackout. So whenever system blackout happens, obviously the system reliability reduces, right? Because let's say DVDC and DESCO are the power system provider. If they can provide power to the customer continuously and smoothly, then actually obviously their reliability will reduce, right? That's why another consequences is that the system reliability reduction. Okay. So we have discussed these 6 points. If you have any questions up to now, you can ask.
So what is the difference cascade outage and system
Blackout. Cascade outage is actually one kind of phenomena that for one transmission line is getting overloaded, there are other transmission lines which will be affected, and gradually those lines will be overloaded and those lines will be in the those lines will be disconnected. Okay. So this phenomenon is called the cascade outage. So if the cascade outage occurs and all the transmission lines are broken down, at that time all the loads will be in the outage condition, and that phenomenon is called the system blackout. System blackout means in this system no load is actually getting any power supply from the generator. Okay. That is the complete system blackout.
So these are not independent events, they are series of consequences like that.
Events are cascading also. Further, the line should be
Yeah, the line should go always the line. Though these scenarios are very actually if actually this limit actually exceeds, then this line will be damaged. It will be usually easily damaged. We have to actually replace this power system provider, let's say this for EPC or this for another power system providers present in our country, for them the reliability will increase, right? So this is actually a reliability issue, right? If we are not getting proper power supply from the provider, then what is the reliability? Okay? That's why I am saying that this is the system reliability reduction. So if you do not have the question, I am giving you 2 minutes there. You can process the things that I have discussed. Okay? And in these 2 minutes, I will take your attendance. Some students are joining late. I have observed in other sections as well. Maybe sometimes I will take the attendance at the beginning of the class.
বোঝা যাবে নামলেও আমি হলো মানে ডাইরেক্ট চলে যাবো না আমার এরকম এখান থেকে নিচে রেখে আসছি হলে
4, 5, 6, 7, 8, 9, 10,
Yes, sir.
11,
Yes, sir.
12,
Yes, sir.
13,
Yes, sir.
14, 17, 18,
Yes, sir.
21, 22, 23, 24,
Yes, sir.
25,
Yes, sir.
26,
প্রেজেন্ট স্যার
27, 28, 29, 30,
Yes, sir.
31,
Yes, sir.
32, 33,
Yes, sir.
34,
Yes, sir.
36,
Yes, sir.
37,
Yes, sir.
38,
Present, sir.
39,
Yes, sir.
40,
Present, sir.
41,
Present, sir.
42,
প্রেজেন্ট স্যার
46, 47, 48, 49, 50, 51,
Yes, sir.
52,
Yes, sir.
53,
Yes, sir.
54,
Yes, sir.
55,
Yes, sir.
56,
Yes, sir.
57,
Yes, sir.
58,
Yes, sir.
59, 60,
Yes, sir.
62,
Yes, sir.
64, 65. Yes, what about this point? What is one? Up to now, we have only considered the real power demand and real power generation. As well as there we have some reactive power demand and some reactive power generation from the generator. Let's think about the industry of factory. In the big industry or factory, loads are the inefficient. Because there are many induction motors and fans, fans, conveyor belts. This type of things actually are consuming inductive power from the system. Okay? And they are actually inductive. So there should have some reactive power demand in your system. Okay? And let's see that there will be some QT or the reactive power generation from the generator. Okay? Whenever we discussed about the real power issues, our generator was actually getting in the stable period when it is connected. Similarly, while discussing this voltage column, we think that let's say this generator is again in shutdown mode, again disconnected. Okay. So maybe again there will be some transmission line failure. So it will not be possible to meet the reactive load demand completely, right? So if there is any mismatch between the reactive load demand and the reactive power generation, at that time our voltage will collapse. Because we have already studied that our V and Q are actually related, right? So if there is any mismatch between the reactive power generation and demand, then it will affect the voltage profile. Okay. If you do the calculation in power unit, you know that 1 power unit if somehow our voltage profile gets below this 0.91 mV or above this 1.1 mV, at that time we can think that our system voltage can be collapsed anyway. Okay. So this is the voltage collapse. Actually, this is the voltage system. Okay. Same thing. Whenever there is a mismatch between the electric power demand and the generation, it is the AC and DC. Then the system frequency variation. So we know that frequency is related to the real power demand. So if there is any mismatch in real power demand and real power generation, at that time the frequency will either increase or decrease, right? So there will be some frequency variation. So this is here, this is this type frequency is stagnant. Okay. So if the frequency varies, what will be the effect? Okay. So let's take one example. Let's think about one Holdings or Levi's company. Okay. In this type of companies, there are like this mechanism. Let's say this is one pipe. Okay. There are some openings or nozzles. Yeah. Okay. Then below there are conveyor belt. Okay. So there are some wheels which are operated by wheels, and this conveyor belt actually is operated by the industry. Okay. And let's say there are some bottles here. So whenever this is rotating, right? So some bottles are giving after filling the liquids, then again the bottles are coming, right? And whenever the bottles are here, this opening are open, okay, and the final form of the liquids are coming out to fill up these bottles. Okay, this is the way. Okay, and this is controlled by this induction motor. It has some speed. This is speed and this is speed to be synchronized, right? So this is simply the sensor. It has been given some instruction that after this amount of time you will do it. Okay, like this, and this is controlled by this induction motor. So induction motor should have some speed, right? And that speed actually depends on the frequency, because if the frequency changes, the motor speed will also change. If the frequency changes and the motor speed changes, so the synchronization will be lost, right? So maybe this opening will be open, but there will be no bottles. So the liquids will not coming inside the bottles, or actually it is coming outside. So this is a huge capital loss in terms of the industry, right? So the industry owner has to take this loss due to this issue, right? That's why the industry power frequency should be within some place, so that there is not any this kind of issue. Yeah. Actually, this is the complete system frequency. That is the 50 hertz, the nominal frequency. If it changes so much due to the mismatch between the real power demand and real power generation, then maybe our frequency will fall or rises to a higher extent. Let's say 49.5 up to 50.5 is the allowable range for frequency, right? If it goes below the 49.5, if it goes above the 50.5, then there are this is the system derivative reduction. Here it is three types. In this course, we will not study the voltage stability and the frequency. Okay, because these two topics are very advanced topics. Okay, these two topics are actually studied in the AC or AC reduction. Okay, we will only discuss about the total angle stability. And what is total angle stability? We will have two types of disturbance. One is small disturbance and another is large disturbance. Small disturbance means steady state stability, and it means the transient stability. Okay. So the last class I already discussed about these two types. So in the next slide, we will study about the origin of the synchronous machine. Okay. Then in slide 3, we will talk about the small disturbance stability or steady state There also we will assume that as prototyping study. Okay. And then we will study about the two machine system. That will actually cover our course content. There will be only one remaining, that is called the economic load distance. Okay. So what is this? Load distance means load distribution among different generators. Okay. So let's say here the total load demand is 20 kilowatt. So from which generator you want to take how much amount of power, that should be your function, right? So if you can operate it, or if you can do it in a most economic way, then you can save the operation cost, right? So your total generation cost will be minimized. That is your main target. Let's say you are a owner of a power producing company. Okay, so you buy fuels from outside, you burn those fuels, and you convert the mechanical energy to the electrical energy in the generator. Then you actually sell those electric energy to the market. Okay? Then your target will be to minimize the generation cost. Okay? So each of these generators have some fuel cost coefficients. Okay? So it is actually varied from generator to generator. So let's say this generator 3 has the higher fuel cost coefficients, and this generator 1 has the lower fuel cost coefficients. So your target will be to produce as much power possible from this generator 1, right? So let's say your demand is 200 kilowatt. So you want to get from the complete 200 kilowatt generation from this generator 1, because here the fuel cost coefficient are less. Means that to produce 1 kilowatt energy, it will produce it at a cheaper rate than this generator. Okay. But there are some limitations or constraints. So in the power system optimization terms, we will say these things as constraints. Like there are some minimum and maximum limit of generation for any generator. Let's say the maximum limit of generation for this generator is 100 kilowatt. So, okay. Though the load demand is 200 kilowatt, you can supply more than 100 kilowatt from the generator. Okay. So there are some constraints or limitations. Okay. So there are other constraints like you have to somehow match the total generation with the demand as well as the loss. That means your generation should be equal to the demand plus loss. Okay. Then there are some equations. For this, there are some inequality constraints. Okay. So for 3 generators, there will be 3 inequality equations. This is 1 equality equations. Okay. Then you have to solve. Okay. After solving, you will get the optimized load dispatch. Okay. From this generator, we can supply this amount of power. And for this is the actually most economic factors where we can actually minimize our total generation cost. Okay. So this will be discussed in a separate slide on the ELT of the economic load dispatch. Okay. So I am just